For January 21st. Let's go ahead and get started with a do now that will have us converting an equation into a graph, a table, and a pattern. You can just do this in your notes. If you have graph paper, it can be very helpful. You put the date up there in your notes. I think that's always useful. Oops, let me plug this in. All right. So looking at the equation, I can go straight to the graph if I want to by using this as my y-intercept and this as my slope. And I don't need to really calculate anything. I just know that this is the point where I'm going to cross the y-axis, so I need to put a point right there on the y-axis. And a slope of 2, well, remember, slope is rise over run. So I need to make a rise over run that equals 2, so the simplest way would be 2 over 1. So that means that from this point, I can rise 2 and run 1, meaning go 1 to the right. Rise 2, run 1. All right, I'm off the graph this way, so I can reverse that. I can go down to left 1, down to left 1, and I can keep doing this for a while until I'm off the graph on this side. All right, and with an equation like this, we should connect it up with a solid line, because there's no reason why we can't be at these decimal values in between the points. So let's connect these up with a solid line. And that's how we graph an equation without the help of a table. Now, if you need the help of a table, that's okay. You just start with a t table like this with an x and a y at the top. Pick some reasonable values to go down the x side. This one's already filled in with -3, -2, -1. So it's just counting up by ones. And then plug these numbers into our equation to get y values. So right here, this would be y equals 2 times -3 plus 3. So these values are coming from the equation, but the -3 is replacing x because we're across from the -3. Now we get y equals -6 plus 3, y equals -3. All right, let's do another one. We'll find this one right here. Y equals 2 times -2 plus 3. Y equals -4 plus 3, y equals -1. We'll put a -1 right here. All right, there's a quicker way to fill in this column if as long as the x's are counting up by ones, as long as these changes are plus ones, you can just keep adding the slope to each number to get to the next number. So add a 2 to -1 and we get +1. Add another 2 and we get 3, which is very good because that is our starting value. Add another 2, we get 5. Add another 2, we get 7, add another 2, we get 9. Now we could have used this to create the graph because this contains a bunch of ordered pairs, if we just add parentheses and a comma in between, that can be plotted. Like let's look at 1, 5, is that on our graph? Go to the origin, I go over 1, I go up 5, yes, that's on the graph. Now with the pattern, you can have some fun with this. All you need to do is make sure that figure 3 has 3 blocks, so I'm not going to have fun with it. I'm going to do a nice boring 3 blocks next to each other. Figure 1 has 5 blocks, but we want to add 2 blocks in a predictable way. So I'll start with my 3 and then just add them to the top. Very boring. Figure 2, I need to copy figure 1 and then add 2 more blocks. And I'll just keep adding them on top so that it's a predictable pattern. And then figure 3, I got to redraw figure 2. And then add 2 more blocks on top. Not my best 2 blocks ever. Let's redo that. All right. Goal for today is to be able to tell the difference between linear and nonlinear relations in the form of tables, graphs, and equations. Why most of the math we're learning is about linear relations, so we need to be able to identify those. All right, because if you're not dealing with a linear relationship, we can't do things like calculate slope or make predictions using y equals mx plus b. All right, so here's the trick on telling if a graph is linear. You don't have to sketch all of these, maybe just a couple, but linear graphs should make a single straight line. Single straight line. So this very first one, this is a very classic linear equation. This is good. 1 second, I want it green. This one is definitely a linear equation. This next one, that's not a straight line, that curves. This one's actually a cubic function, which is not a type of linear function. So this one doesn't work. Another one that curves, that one doesn't work. Another one, it curves, that's not linear. This one curves, that's not linear. This one, straight line, it's got a negative slope, but that's okay. That still is a linear equation. This is a line just made out of dots. Now you might say, well, it doesn't look like it's a perfect line, but we'll pretend that that's a perfect line. So you don't have to have all the dots. But what about this last one? It's V-shaped. I'll embed a question here. What do you think? Is this one linear or nonlinear? All right, the correct answer is nonlinear because it's a single straight line. This is two straight lines with an angle, so that makes it nonlinear. If you just zoomed in on half of it, then it would be linear, but if you have both of the lines, then it's nonlinear. Okay, so now let's deal with how to spot it in tables. So the trick to tables is that delta y over delta x needs to be constant. All right, and delta y are those little bumps down here going down the y side, and delta x, so that's delta y over here, and delta x are the changes on the x side. So how much we change over here. All right, so let's write down all of these. To go from 0 to 1, well, I just add 1. 1 to 2, I add 1. 2 to 3, I just keep adding 1. So that's consistent. Let's check on this side. 10 to 12, that's a plus 11. 21, or not 10 to 12, 10 to 21. 21 to 32 is plus 11. 32 to 43 is plus 11. So if I divided these, I'd get the same fraction every single time, and that means, yes, this is linear. We'll highlight that. So you probably copy down at least two of these. Try to copy down a linear and a nonlinear one. All right, let's look at this table over here. So on the x side, we go plus 3, then plus 3, then plus 3. Okay, so that's constant. Over here, we go plus 4, plus 4, plus 4. So yes, if we kept dividing those pairs of delta x and delta y, again, it'd be the same number every time. That's another linear table. All right, let's look at another one. This side, it's going plus 1, plus 1, plus 1. What about this side? Plus 6, plus 5, plus 5. So that's not constant. It doesn't go 1, 1, 1, 5, 5, 5. It goes 6, 5, 5. And that's enough to make this non-linear. So we're going to fill in the thumbs down. It's not linear because of that slight change there. It needs to be exactly the same each time, or simplified to the same fraction each time. All right, let's look at this one. So we're going minus 1. That's fine. We can have minuses and still be linear. Minus 1, minus 1. And then on this side, it goes plus 1, plus 2, plus 4. It looks like it's actually being multiplied by 2 each time, but that doesn't count as being linear. It has to be addition that's constant. So again, we have a non-linear. In my highlighter. So this is another non-linear. Okay. Now let's talk about equations. What makes an equation linear versus nonlinear? Well, here I've got a bunch of linear equations and a bunch of nonlinear equations. I'll embed a question here for you to type what you think is different about this column and this column. All right, so what we should have picked up on is that linear equations, when simplified, because you need to simplify before you can even evaluate it, do not have exponents bigger than 1. All right, and that's, if we look at this, we don't see any exponents, but we could technically put a 1 in above all of these x's, because when you just have an x by itself, there could be an invisible 1 up there that doesn't change anything. So linear equations, when simplified, do not have exponents bigger than 1. But really, they shouldn't show any exponents because when you simplify it, you'd get rid of that 1 if there wasn't 1 there. All right. Also, no x's in the denominator. If your equation is a fraction, the x has to be on the top for it to be linear. So let's practice with this a little bit. Let's just practice sorting some equations. I'll write the equation you think whether it be linear or nonlinear. So y equals 7x plus 4. This is linear. Yep, this is our classic linear equation. All right, it's even in y equals mx plus b form, which is always a linear equation. All right, what about just y equals 5? This also counts as linear. It doesn't have to have an x. This would just be a straight horizontal line. What about y equals x squared plus 3x? This is nonlinear because we've got an exponent there that's bigger than 1. All right, what about y equals 1 over x plus 3? This is another nonlinear. All right, x can't be in the denominator or the bottom of any fraction, or else you'll get this very interesting curved graph. All right, I think that's that for this. I'll embed a few more questions here, but have a good rest of your day.